Hello everyone, this is Mr. McMillan and I'm back with part 2 of the changes in scale instructional video, and this time we're going to be talking about changes in scale in three-dimensional figures. So with three-dimensional figures, changes in scale affect the surface area and volume. Okay. So unlike with two-dimensional figures, the three-dimensional changes in scale are much more reliant on their formulas. So when we look at examples of these, we're going to analyze the formula before determining how much the surface area or volume has been changed. Of course, if everything has been tripled or doubled or quadrupled or whatever else, we can use those ratio of sides because those would be similar figures like we talked about in a couple of videos ago. So on number 1, it says for the rectangular prism below, if the side lengths are tripled, what would be the ratio of the new volume to the old volume? So just to get you acquainted with how I'm doing it with the formulas, we're going to talk about what it wants. It wants the volume ratio. So our initial volume is going to be length times width times height. That's our old volume. So in this case, it would be 1 times 3 times 7. Now what we're going to do is it says the side lengths are tripled, and it doesn't say anything about just one or two of them being tripled. It means all of them. So what we're doing is tripling the length, width, and height. So our new volume is going to be 3L because we tripled the length, 3W because we tripled the width, and 3H because we tripled the height. Well, 3L, if we take the numbers in front, we take 3 times 3 times 3, which would be 27, and then that leaves behind length times width times height. So what is the ratio of the new volume to the old volume? Well, if we were to put this in a ratio, the new volume is 27, length times width times height, and the old volume is just length times width times height. On the bottom and on the top, the length times width times height cancels, so that just gives you 27 over 1, which means your ratio of the old volume to the new volume, or rather backwards, is 27 to 1. Now the other way we could have done this, the side lengths are tripled, so that means our ratio is 3 to 1. And we can say that because all of the side lengths are tripled. Now we're going to the volume. So the volume is in cubic units. And so since it's in cubic units, we're going to cube 3 and 1. So 3 cubed and 1 cubed. 3 cubed is 27. 1 cubed is 1. So we got the same thing with two different methods. So it looks like we're good. All right, let's look at number 2. For the cube below, if the side lengths are doubled, what would be the ratio of the new surface area to the old surface area? So for this one, I'm going to be doing it using the ratios. So the side lengths are doubled. This is a cube, so if you double one side length, you double all of them. Okay, so that means the ratio of our side lengths, or our scale factor, is 2 to 1. Now it wants the ratio of the new surface area to the old surface area. Well, surface area is measured in square units. All right, sorry about that. So our ratio of the sides, our scale factor is 2 to 1. And we're looking for the surface area, and the surface area is measured in squared units. So we're going to have to square our side ratio. So we do 2 squared and 1 squared, just like we did when we did similar figures. And when you do that, you get 4 to 1. So the ratio of the new surface area to the old surface area would be 4 times as large. All right, let's look at number 3. Number 3 says a cylinder has a radius of 6 inches and a height of 9. If only the radius is quadrupled, so only the radius is quadrupled, what is the ratio of the new volume to the old volume? So first off, are all the dimensions being affected, or is it just one? Well, one of the cylinders that we need. Well, here, only one of the cylinders needed ones to find the volume is affected, and it's quadrupled. So the new radius is going to be 4 times the old one. So we need to do our formula method like we did here. So the volume of a cylinder is given to us by pi r squared h. Now what we're going to do here is we're going to quadruple what r is. So we have pi, in parentheses, we have 4 times r because we're multiplying it by 4. And then we have a squared. So this is your new radius. That's why it's in the parentheses and it's still squared, times your height. So 4 times r, in order to get the 4 out of the parentheses, you have to square it first. And so that gives you 16 pi times r squared h. And then you take 16 pi r squared h divided by pi r squared h. Basically, you're knocking off what's in common. And so your ratio of the new volume to the old volume is 16 to 1. Okay. All right. Number 4, it says a cone has a radius of 3 feet and a height of 5 feet. If both dimensions are tripled, what would be the ratio of the new surface area to the old surface area? So in this case, it says both dimensions are tripled, so both the radius and the height are tripled. So we can use a scale factor for this one. So a scale factor here, we have a radius of 3 feet and a height of 5 feet that both get tripled. So our scale factor is 3 to 1. Since these are similar figures, we can determine the area or the ratio of the areas now by doing the appropriate either squaring or cubing. Surface area is measured in squared units, so we're going to square both 3 and 1. So this becomes 9 to 1 as our new surface area to the old surface area. All right, number 5. For the sphere below, if the radius is quadrupled, what would be the ratio of the new surface area to the old surface area? And then what about the volume? Now this one might confuse you a little bit, but let's look at it in a little bit more detail. It says the radius is quadrupled. Now you may be saying, well, that's only one dimension. But if we look at our formulas for surface area and volume, the only thing we need in those is the radius. So this actually turns out to be a similar shape situation. And in fact, all spheres are similar. All spheres are similar. So our scale factor, since it's quadrupled, would be 4 to 1, quadrupled meaning times 4. We're going to find our surface area first, a ratio of the surface area. Surface area is measured in squared units, so we're going to square the 4 and the 1. 4 squared is 16, 1 squared is 1. Then we're going to do the same thing to find the volume. So our volume you have to cube because it's measured in cubic units. 4 cubed, 1 cubed. 4 cubed is 4 times 4 times 4, which is 64. 1 cubed is 1. So our ratio of the surface area is 16 to 1, and the ratio of the volumes is 64 to 1. All right, number 6. A rectangular prism has a length of 4, a width of 8, and a height of 12 inches. If only the width is tripled, only the width, what would be the ratio of the new volume to the old volume? So this is a case where we have 3 different dimensions we need and only one is being tripled or quadrupled or whatever. So our original volume is going to be length times width times height. Now our new volume, the length is untouched, but it says the width is tripled. So we're going to multiply it by 3. And then our height is unchanged. Okay, so the length times 3 times the width times the height. And when we simplify this, we get 3 times length times width times height. All right, so could you tell me what the ratio of the volumes would be now? Well, if we did it like the way we've been doing the other ones, we have 3 length times width times height divided by length times width times height. Those length, width, height are the same. So this is 3 over 1, which gives us a ratio of 3 to 1. And then the last one we're going to do in this video is number 7. This should say a rectangular prism has a volume of 65 inches cubed. Answer the following. If only the height of the rectangular prism is doubled, what would be the new volume? So we need to determine the ratios of the new volume first. So our old volume is length times width times height, and it says only the height is doubled. So this is going to be length times width times 2h, which gives us 2 length, width, height. So our ratio, this new volume is twice as large as the old one. So our ratio of the volumes is 2 to 1. So that means our new volume must be twice as large as our old volume. Well, our old volume is 65. And then we have to multiply it by 2 to get 130 inches cubed. Then the last one asks, if all dimensions are doubled, what would be the new volume? So this time, all dimensions are doubled. So we start out with the ratio for the scale factor. And we want to know the new volume. Well, we'll have to take 2 and 1 and cube them to get 8 to 1. So this means that the volume of the new one must be 8 times as big as the volume of the old one. So we take our old volume times 8, and when we do that, we get 520 inches cubed. And that's going to do it for this video, guys. I hope this video has helped. Please work on T10, T11 as explained in the Google Classroom. If you have any questions, please let me know. You know, we're going to go over some more examples of questions like these, as well as the ones on T9 in the future, most likely in a video going to be posted very soon. So thanks, guys, and I will see you in the next video.